Welcome. In this session, we will explore InfiniBand, a specialized networking architecture designed to meet the extreme demands of high-performance computing and AI. Let's begin by understanding why it was built. To understand InfiniBand, we must first look at the problem it solves. Traditional shared bus architectures force all devices to compete for the same bandwidth, creating a bottleneck as you add more devices. InfiniBand changes this paradigm entirely. It is a switch-based point-to-point fabric, meaning every connection gets dedicated bandwidth. This architecture was explicitly designed to provide ultra-low latency and low CPU overhead, ensuring that the network doesn't slow down faster processors. It effectively extends the system's I/O bus outside the server chassis, allowing you to connect thousands of nodes with the same efficiency as internal components. On the left, we see a traditional shared bus architecture. Notice how the CPU and all devices share a single communication line, leading to contention and bottlenecks. On the right, we have the InfiniBand fabric. Here, nodes A, B, and C connect directly to a central switch. This point-to-point design ensures that each connection maintains dedicated high bandwidth without fighting for resources, enabling the scalability required for modern supercomputers. InfiniBand functionality is defined by a structured, layered protocol stack, much like the OSI model but optimized for hardware efficiency. At the core of its performance is the link layer, which uses 16-bit local identifiers, or LID, to switch packets rapidly within a subnet. Crucially, InfiniBand employs a credit-based flow control mechanism. It means a sender will not transmit a packet unless the receiver explicitly signals that it has the buffer space to accept it. This guarantees a lossless network where packets are not dropped due to congestion, a critical requirement for maintaining the performance of tightly coupled HPC and AI workloads. This sequence diagram illustrates InfiniBand's credit-based flow control. The receiver first tells the sender it has 2 credits, presenting available buffer space. The sender transmits packet 1 and packet 2, exhausting its credits. Crucially, the sender then automatically stops transmitting, preventing a buffer overflow and packet loss. Once the receiver processes the data, it sends new credits back, allowing the sender to resume. This hardware-level conversation ensures data is never lost due to congestion. Truly sets InfiniBand apart for AI is how it handles data. It natively supports remote direct memory access, or RDMA. This allows data to move from the memory of one server directly to another, completely bypassing the CPU and the operating system kernel. This zero-copy approach drastically reduces latency. Furthermore, InfiniBand enables in-network computing, such as NVIDIA Sharp. Instead of moving data back and forth between nodes to perform calculations, the switches themselves perform collective operations like data reductions. Combined with adaptive routing, which dynamically steers traffic around hotspots, InfiniBand transforms the network into a coprocessor. Here we compare data paths. The top path shows a standard network where data must pass through the OS kernel, adding latency. Bottom path shows the InfiniBand RDMA approach. Data moves directly from application memory to the host channel adapter HCA, bypassing the CPU. The data then hits the switch, where Sharp technology can perform calculations on the fly aggregation, delivering the final result to the remote HCA. This offload architecture is the key to InfiniBand's speed. Finally, InfiniBand was designed for scale and reliability. It operates as a full software-defined network, controlled by a centralized entity called the subnet manager. The subnet manager sees the entire network topology and programs optimal routing paths for every switch, ensuring no loops and efficient traffic distribution. This centralized view enables advanced RAS features reliability, availability, and serviceability. If a link fails, the network has self-healing capabilities to instantly reroute traffic. This ensures that mission-critical simulations and AI training jobs continue running smoothly, even when hardware components fail. This state diagram represents the life cycle of the subnet manager. It starts with discovery of all nodes. It then performs calculation to determine optimal routes and pushes configuration to the switches. It enters a monitoring state. If a fault is detected, such as a cut cable, it immediately transitions to self-healing, calculating new paths and reprogramming the fabric to reroute traffic before returning to monitoring. This loop ensures continuous availability.